Welcome back to Kiersti's virtual classroom. Today we are talking about water pollution. Let's go ahead and get started. So why is water important? Well, water is important because it's essential to all life on Earth, not just humans, but any life that exists, it is essential. It is our most valuable resource, and water dissolves the nutrients and distributes them to cells, regulates body temperatures, it supports structures, and removes waste products. 60% of your body is water, and you can survive weeks without food, but only a few days without water. So water is everywhere. 70% of Earth's surface is covered in water. So that's why we are known as the blue planet, because when you look at Earth, most of what you see is water, which is blue. But we have a problem. 97% of that is locked in our oceans. Oceans are a problem because we cannot drink ocean water without desalinizing it. So without removing the salt content in ocean water, we can't drink it. And then another 2% of our water is locked in glaciers and polar ice. 0.62% is in groundwater. So that's important because that's where most of our water actually ends up coming from, is groundwater. And 0.008% is in lakes and rivers, so our surface water. And then 0.001% is in our atmosphere as atmospheric gas, or as water vapor. So that 1% that we can use of surface water and groundwater, we use it for everything. We use it for drinking water, agriculture, transportation, steam power, and a lot of other things. So we have 1% of potable water on Earth that we can use. So who uses the most? So this is a little different than some of the other pollutants that we've talked about. So when we're talking about like petroleum consumption, industry uses a lot more, but as far as water consumption goes, agriculture uses the most. Industry uses the least. And then domestic use, so household use, is right in the middle. So looking at it a little differently, about 60% of the water usage on Earth is agricultural related. 25% is in the home or domestic use, and 15% is used in industry. How do you use your water in your home? So this kind of diagram will depend on what you do in your particular home, but upwards of 30% of your water usage in your home is from flushing. So flushing the toilet. So go to the bathroom less. Or you can do the meet the parents method where they only flush it if it's number 2. If it's yellow, let it mellow. If it's brown, flush it down. And that helps use less water. It's not super sanitary, but it uses less water. And then baths and showers are about 35% of your consumption in the home. If you take less baths or shorter showers, obviously this will decrease for you. Laundry uses about 20%, so filling up your entire drum washer, and then all of that after it finishes washing the clothes will get pushed out and into wastewater. And then 10% is drinking and cooking, and 5% cleaning. So all of these can kind of change depending on your habits in your home, but this is typical. You are lucky though, because you can turn on your faucet in your home and clean water will come out. But a lot of people in a lot of parts of the world lack the access to potable water. Potable water is water that is drinkable without having to change it at all. So 2/3 of the world's households have to fetch water from outside the home. So they have to walk to a stream to get water. Improved public systems bring many benefits to these poor families. So there has been an increase in potable water access in some of these countries, but it's still not as great as if you live in California and can turn on the faucet and it's going to be clean drinking water. So consumption is drying up our freshwater systems. So we see a lot of areas in the Central Valley that have dried up significantly. We don't see a lot of surface water. other than maybe in canals. And there is a drought that kind of cycles through the Central Valley every few years, and we have a very low water availability in the Central Valley. This is similar to what's happening in Kazakhstan and Uzbekistan. So this is the Aral Sea from 1977 to, this is 2010. So from 1977 to 2010, there has been a drastic depletion of this surface water body. And one of the things that you'll notice is as more water is pulled out, you'll see kind of these white areas develop. That is all of the excess salt that is left behind after water is extracted, and we call these evaporites. So this is the product of the evaporation process, what's left behind. It's usually a very high salt content, and then eventually this will be undrinkable because there's too much salt in whatever's there now. So the water cycle is important. We need the water cycle to live. One of the issues is that water can get trapped in specific areas. So right now we have a lot of water trapped in the ocean, and without evaporation of the ocean surface, we won't get condensation and then precipitation, which is where we can get the water. So we can get water from the runoff into our surface waters, or the infiltration into groundwater, which we can then extract. But if that flows out back into the ocean, we won't necessarily be able to use it. So surface water is any water that is precipitated onto the ground and is not absorbed into the ground and will run off as fresh water storage. So surface water is water on the surface. So this would be streams, rivers, lakes, things like that. And we can drink from these water sources, but oftentimes we have to clean them in. We have things like surface water treatment plants that help clean out any pollutants that might be in the water before we send them to the distribution system to come into your sink. So surface water and infiltration and runoff, when precipitation occurs, the water will either infiltrate or run off. If it runs off, it becomes part of the surface water system. So it either runs off as a stream, a river, or something like that, and then can flow into the ocean, or it can infiltrate or percolate into the ground and become groundwater, which usually stays in the ground for a significant amount of time before it's pumped out and used. So water runoff, like I said, are in rivers, lakes, small streams and creeks, storm drainage, flooding. Urban surface water runoff happens when it hits the street, and then it goes into our storm drains, and then it goes in the Central Valley in particular, our flood basins. So you've probably noticed big basins that hold water around town. Those are fed by the storm drains that you see on the side of the sidewalks and streets that collect any rainwater. So runoff can be damaging depending on what is happening in an area. So here is an example of a stream that comes from two locations in a mountain area. So this area over here on the right looks pretty clean, but over here on the left, it looks very dirty. And this contaminated surface water is then contaminating the whole stream. So whatever is happening upstream, whether it be construction, mining, whatever, is disturbing the surface water runoff and is causing pollution to this surface water body. So deforestation increases runoff and decreases infiltration. So the more plants and trees and things like that you have, the better your infiltration will be into the groundwater. And that's really where you want most of your water to go, because the ground has a very great natural filtration system built in. Whereas as soon as it hits the ground, if it starts running off, it has more chance to pick up more ground pollutants on its way. So the more deforestation you do in an area, so if you remove a bunch of trees, you're going to see less infiltration and more surface water runoff, which will also increase your surface water pollution. So things that influence water infiltration are precipitation, the base flow that you have, so how much water is already on the surface, soil characteristics, soil saturation, so if the ground is already saturated, more water can't fit in, land cover, so do you have deforested lands, do you have a large vegetation in this area, the slope, so the steeper the slope, the more likely the water is going to run off instead of percolate or infiltrate, and then the evapotranspiration. So water infiltration can be affected by porosity and permeability. So the material or the subsurface materials below the surface will either have a high porosity or a low porosity. So the porosity is the volume of open spaces in a rock or soil. So if we have a high porosity, that means that water can fit in to the pore spaces between the grains or between the rock or soil very well. And this can be pore spaces, fractures or joints, vesicles, cavities, any opening in the rock or soil is considered the porosity. Permeability is a material's measure, or a measure of the material's ability to transmit that water. So if it has a high porosity, it'll oftentimes have a high permeability. So these kind of go hand in hand. So permeability is the ability to transport water, and porosity is the open spaces. So we want it to have a high permeability. We want the subsurface to have a high permeability so that water can infiltrate. Things that have a low permeability will not allow water to come in. So here's an example of what permeability would look like in different types of materials. So here we have a gravel, a sand, a silt, and a clay. Clay is a very small sediment size, and it will take upwards of 200 years for the same amount of material or same amount of water to flow through the same amount of material versus gravel, which would take 2 minutes. So depending on the subsurface material, if you have a lot of clay, you'll see water pool at the surface more so than infiltrate. So in places like Tulare, that used to be a giant lake basin which had a lot of clay. So there's still a lot of clay in Tulare, and they have poor infiltration into their ground. When we have surface water, you see a lot more pooling out there. Whereas in Reedley, they have a lot more sand and gravels because they're near Kings River and they're near the mountains. So their infiltration is greater in Reedley than you would see in Tulare. So here's a look at porosity. So porosity, like I said, is the pore space between the grains, depending on whether you have all of the same size, different sizes, or maybe you have some cement holding some of the grains together, that will increase or decrease the porosity. So if you have a bunch of marbles in a jar, for instance, the porosity would be higher than if you had those same marbles plus sand in the jar. So this on the left would be a bunch of marbles in a jar with water, and then on the right here would be a bunch of marbles with some sand particles that are smaller that can fit into the spaces between the marbles. And that will decrease the porosity, which will decrease the permeability or infiltration of the water into the ground. So some porosity factors are rounding, sorting, and cementation. So the rounding is how round the grains are. So if the grains are very well rounded, you're going to fit more water in those pore spaces. You're going to have more pore spaces, higher porosity. If it's poorly rounded, so it's angular, it's going to fit together, the grains will fit together more like a puzzle piece. And then the water, as it infiltrates into the ground, doesn't have as many spaces to fill. So it would be a lower porosity if they are poorly rounded. Now, sorting is the sizes that I was talking about. So if you have all marbles, there's a lot more spaces between the grains because they don't fit together like a puzzle piece. But if you have two different sizes, you have marbles and sand, the sand will fit between the pore spaces in the marble, and then less water can fit in. So if you have poorly sorted, so it's a bunch of different sizes of grains, you're going to see less porosity or a lower porosity material. If they're well sorted, so they're all about the same size material, you're going to see a higher porosity. And then cementation occurs as well. So some material is cemented together into a rock. If that's the case and it's well cemented, you're going to fit less water in it. If it's unconsolidated sediments, like what lies beneath most of the Central Valley, you're going to have no cement and you're going to fit more material or more water into the pore spaces in the grains. All right, so this is an example of permeable pavement. So one of the issues in urban surface water runoff is that a lot of the surfaces that we create are not permeable. So asphalt, concrete, these things do not allow water to permeate through them and then go into the ground below them. So there's something called permeable pavement that has been developed. And you see this a lot in San Diego. You'll see it in some parts of LA. They have it in Santa Barbara. Sacramento's starting to do it, to where you get the water to percolate through this pavement so that water doesn't get stuck on the surface and then clog up our drains. So the speed test is pretty interesting to watch. Hopefully it'll work. There we go. Okay, so this is, one second real quick. So this ice chest is filled with water, and this ice chest is filled with water. One is on the drain, which is impermeable concrete. This one on the right here is on the permeable pavement. Okay, and you can kind of see what's happening. So water is flowing down this impermeable concrete, and the water is flowing into the permeable pavement. So the water here is allowed to percolate into the ground beneath the pavement, whereas this other one here just flows into the storm drain and is now backing up the storm drain here, as you can see. And so this causes a lot more issues with runoff, right? So if we have more permeable pavement like this, then we would see more infiltration into the ground in urban areas. Here's another look at it. This is in a parking lot. Water starts spraying a significant amount of water onto the ground, and it's not even coming up halfway into the driveway space. So the water is percolating really well into the pavement and then going into the ground. Now, one of the issues when we were talking, when we were on this little field trip, we were talking to the people that develop it, is that it will get filled, these holes will get filled with dirt and debris and leaves and things like that. So they do have to do more maintenance on it and clean it out, kind of suck out all of the dirty stuff. That way the water can still percolate through. But this is a really good development. Instead of water running off, it can now percolate into the ground. And you'll see less surface water storage, but you will see an increase in our groundwater levels. All right, so let's look at groundwater. So this is what happens when the water hits the surface, percolates into the ground. We then are looking or focusing on groundwater, which is really important when we're talking about drinking water and when we're talking about how water works in the Central Valley. So after infiltration occurs, there are a few different zones that the water can sit in. So the first zone it would encounter is the zone of aeration. So this is the area above the water table where openings in the material are filled with air and water. So this is where water is being transported from the surface here all the way down into the groundwater. So the capillary fringe is a narrow zone just above the water table where water is being pulled upward. So just like with anything in nature, water wants to go from an area of high pressure to lower pressure. So as it approaches the groundwater from gravity pulling it down, the water says, this is too high of a pressure zone, I want to go the other way. And so there's a narrow zone above the water table where water starts to try to climb back upward, but eventually gravity is stronger than that threshold and pulls it back down to the water table. The water table marks the top of the saturated zone, which is the bottommost zone in groundwater, which is known as a zone of saturation. So this is a zone where all openings between spaces and grains are filled with water. So any pore space that you see between grains is filled with water. So the water that reaches the groundwater can be stored for hundreds of years in aquifers if it's not pumped out by people. So the aquifer is known as a permeable rock or sediment that transmits water in a quantity great enough to be of use. So just a 5-gallon little section of water is not considered an aquifer. It has to be over a vast area. So in Fresno, we have something called the Fresno Aquifer, which is the aquifer that sits below the area of Fresno. So we have confined aquifers, unconfined aquifers, and then slowing between aquifers. So confined aquifers are overlain by a confining layer, so an impermeable layer. So here we have a confined aquifer down here at the bottom, and there's a confining layer that is preventing flow between this confined aquifer and this unconfined aquifer. Then we have the unconfined aquifer, which is where the water table is the top. So these upside down triangles represent, or they are a symbol of the water table, just an FYI. So the water table is here, where this blue line kind of interacts with the yellow. This is the unconfined aquifer. So it's where water will percolate down and become part of the aquifer. Aquatards will retard flow between two aquifers, and aquicludes will exclude flows between aquifers. So this confining layer here could either be an aquatard or an aquiclude, depending on its permeability properties. So if it's got kind of an intermediate permeability property, it might be just an aquatard where it's just slowing the flow. If it's more like a clay, it's considered an aquiclude, which kind of excludes the flow between aquifers. So when we talk about groundwater interactions, there's something on the coast of California that happens a lot, which is saltwater intrusion. So this is when pumping of fresh water out of a well exceeds the recharge rate. So you're pumping faster than the water can be replenished. And this happens in a lot of coastal areas, and saltwater or seawater will come in and infiltrate into your well. As soon as you see saltwater intrusion or infiltration into your well, you've lost that well. You have to then re-drill the well and more fresh water and try to create a barrier to prevent more salt water from coming into your new well, because you can't drink salt water. So in the United States, groundwater aquifers look different in different areas. So in the northeastern portion of the United States, there used to be a lot of glaciers there. So you see a lot of glacial till, which is material left behind by the glacier. And it's usually a combination of sand, silt, gravel, large boulders. And so that creates a lot of areas where water can sit in the ground, and then we can pull it out of the ground and use it for consumption. In the Central Valley, you'll notice we're very blue, so this is where we have unconsolidated sand and gravel. In the Oregon-Washington area, we see a lot of volcanic rock aquifers. So because we have a very large area of cascade volcanoes that have produced a lot of volcanic rock, we see a lot of their groundwater sit in volcanic rock aquifers. So a lot of people don't actually know how you get water into your home. There isn't a pump unless it is necessary to get the water into the home. Most of the time it is reliant on pressure. So in a particular water level, there is a pressure surface, which is the water level. And if that pressure surface is above where you want the water to go, it will help push the water into those other areas. So water tanks in neighborhoods, this is very obvious at Fresno State. If you ever drive through there, they have a very large water tank. Well, that water tank is tall, so that it's taller than the buildings, and the water level is higher than where you would want water to go into buildings. And the pressure helps push it down into all of these pipes and then into the buildings or into your homes. Okay, so that's how we get water into our houses. So groundwater in the Great Valley, the San Joaquin Valley is on the top, Sacramento Valley is on the bottom. We see much more farming in our area, and we have a lot of what we call land subsidence. So as we pull groundwater from beneath our feet, we see the land start to subside or start to settle more. So over time, as you pump very heavily, you'll get something called a cone of depression, which is where the water is depressed in a particular area. So water is most depressed in Fresno, in southeast Fresno, which is the oldest part of Fresno, the area where we've been pulling groundwater the most for the most amount of years. So heavy pumping will lead to these cones of depressions, which will lower your groundwater, which will then require you to either re-drill or lengthen your well in order to still consume that groundwater. So overpumping causes that subsidence that I was talking about. And basically what happens is groundwater is removed, and groundwater takes up space in the subsurface. So as groundwater is removed, that space then can collapse or consolidate it on itself. And you have the weight of the material above that helps push that down. So you remove groundwater, and this doesn't happen overnight. If the groundwater was replenished at a steady rate, that water would then fill in those spaces where we just removed water. But that doesn't appear to be happening, and we see subsidence of the land, and we are losing elevation. So this happens the largest in southwest Mendota. We've lost 29 feet since World War II. So the land has decreased, the elevation has decreased or settled 29 feet. That's significant. And so here's an example of what that looks like. This is Joe Poland, who is a USGS scientist who looked at subsidence in the Central Valley pretty in depth, and he used this pole for reference. This pole was not around in 1925, but it's just for reference to show you what 30 feet looks like. So from 1925 to 1977, we have lost 30 feet in this area. Now there was some updated photos done, I think a couple years ago, and we've only lost another 4 or 5 feet. It's not that significant as it was between 1925 and 1977. So we've been a little bit more sustainable in our most recent groundwater pumping. So one of the things that I talked about was not drinking ocean water. So we can't drink ocean water, but we can desalinate it or remove the salt water concentration or the salt concentration in the water so that we can drink it. So they are doing this in the San Diego area and the Los Angeles area to try to use some of the ocean water for their drinking water systems. So there are a couple of ways this can occur. We can use distillation or we can use reverse osmosis. So in step 1 here, salt water comes into the chamber, and then the heating element boils the water, creating steam. So this condensation coil here is where the water will then condense the pure H2O without the NaCl or the sodium chloride, which is salt, essentially. And that will, so the steam vapor comes from here. The condensing coil allows for the H2O molecules to condense into a liquid again, and the saltwater-free water can flow out of the chamber, and then the brine, or the salt, essentially, will flow out the other portion of the chamber. Okay, so that's one way that we can remove the salt from the seawater. Okay, the other way is reverse osmosis. So this requires water to come into the chamber, and then pressure is applied to the water to try to push it through this membrane. And this membrane will not allow for salts to come through, but H2O molecules can fit through. So the water will percolate through this membrane, and the salt will get stuck and then eventually flow out. And then the clean water can flow out this other side after it has flowed through this membrane. And so these reverse osmosis machines, each membrane is about the size of a larger kitchen island, and they have a lot of them in a building. So if you ever go to Carlsbad, which is near San Diego, they have a saltwater filtration system all set up, and I think you can do tours of the desalination plant. We did a private tour before it was opened, and then I think they're probably open to the public now. That was like 5 years ago. And they do both of these. So they do distillation first, and then they throw it through reverse osmosis. And then what they do is they put it through kind of a ground filtration system. So they've created a simulation of the groundwater or the ground subsurface and do a filtration system that way. And then what happens is it gets mixed with other water that they use in San Diego in their distribution system. So it mixes with other surface water, groundwater that they have pulled into their distribution system. Some other areas that I've seen, they're pumping it back into the groundwater to mix with the groundwater naturally before it's pumped out. So in the Central Valley, we use a lot of in situ and air sparging because we get contamination of our soil and groundwater from a lot of different means. So some of the ones that I've worked on for the Central Valley include TCE and PCE, which are tetrachloroethylene, and trichloroethylene. And these are contaminants that are found in industrial processes, dry cleaners, things like that. And they can contaminate the groundwater. Other things that can contaminate the groundwater are obviously gasoline. So at gas stations, if the tanks leak, that gasoline or diesel that leaked can get into the soil and then in the groundwater. And the way that you get cleaner water from those areas is to go through something called air sparging, which is where we basically inject bubbles or air into the ground, which the gas will bond with and then come up through these extraction units, and then it can be cleaned as a vapor, and then the exhaust will be a cleaner exhaust, and then we discard all of the stuff that was contaminating the ground or the groundwater. So basically this is adding air into the ground to try to extract the bubbles that contain all of the petroleum product. Another way to do this is pump and treat. So with the trichloroethylene and the tetrachloroethylene, which are contaminants from dry cleaners and from industrial processes, there's huge plumes in the Central Valley or in Fresno that we will pump and treat. So you'll see some of these kinds of tanks maybe around town. I used to work on these tanks. So basically what happens is there's carbon, granulated carbon in these tanks, and water comes into the tank, and the water will filter through the carbon, and the carbon will bond with the trichloroethylene and the tetrachloroethylene products and kind of attach to them, and the water can flow through the bottom here and into the distribution system after it has been cleaned. And then eventually you have to come and refill the tanks with new carbon, and then the carbon has to be treated at a treatment facility itself, and they kind of recycle it, and then they bring it back, and then you do it all over again. So this is what happens in a lot of Fresno before you see any water come into the pipes. So we have a lot of treatment on our water to help remove a lot of these chemicals that have contaminated our groundwater or continue to contaminate our surface water. Okay, so that's it for water pollution this week, and I will see you guys next time. Bye.